In this video, we are going to go over the basics of the protein quantification and Caspase 3 activity analysis. This goes with the assignment that you will have for the protein analysis. It's right here. So you are going to be using the data set that is provided to you within this assignment. And you are going to be calculating all the quantifications using the information I provide to you today. All the data calculations should be done in an Excel file, and then you will be taking those Excel calculated and prepared graphs and putting them into this assignment. Okay, so starting off, I just want to go through some of the basics so you know what it is that you are going to be looking at. The first thing that you are going to do is create a standard curve to use for quantification of your unknown proteins. To do that, you have been provided with a standard protein, a set of dilutions from a standard protein, and you've already been provided actually the concentrations that are in each one of the dilutions. However, I do want you to practice getting those dilution concentrations yourself, given the volume of the diluent, which is the water, the protein, which is listed as Assay, but could be any standard protein, so the amount of protein and the amount of water, and then the stock concentration of your protein, which is the 2 mg per ml. So this is your, my favorite formula, C1V1 equals C2V2, where C1 is going to be your stock concentration of Assay, which is right here, 2 milligrams per milliliter. V1 is going to be the amount of that stock protein that you are adding to a particular dilution. So if you're looking at column 2 or row 2, it will be 10 microliters of the 2 mg per ml. So this would be your V1. C2 is the final working concentration of that dilution, the final dilution, and that would be your X. That's what you're trying to find out. And V2 is going to be the total volume of the dilution that you're preparing. In all these columns, in that entire column and each one of these rows, for each dilution you are preparing 80 microliter total volume. You can get that by adding the amount of the standard protein plus the amount of water for each row, and that will give you 80 microliters total volume. That's going to be your V2. So you would use that to solve for X, and you should be able to get the same numbers as what are listed in your assignment. Next, you are going to be preparing the standard curve by taking away your absorbance that you got for the water only blank, which is just water. There's no protein there, so whatever absorbance you get for that is the background noise, and that's listed right here. So in this example that I'm showing you 2 separate rows as an example. The dilutions are placed from the highest to the lowest values in the first 8 rows, and given that the 8 is actually your tube 1, the water only well, this is your blank. So in the entire row you are going to be subtracting the value that you have for well 8 from all of them. When we are putting this formula into Excel, we write it just like this, where it's an equal sign. You click on the first well that you want to subtract from, minus, and then you click on the well that you want to subtract. Now, because for every single well I want to keep that well constant, I always want to subtract the value from A8, the A8 value from all of them. I will put a dollar sign before the A as well as the dollar sign before the 8. The dollar sign tells the computer, tells the Excel program to keep that constant for the entire, for any well that you're putting that formula in. So for the entire row, in this case. So you would do that. For row E, you would do the same thing. That value will be different because the row 8 value is different, or column 8, A8 is different in this case. In this case, it's E8. So you would write the formula equals E1 minus dollar sign E dollar sign 8. So it keeps that constant for this row. For row E, it would be E instead of A. Okay, so then once you have those blank corrected values, you can plot them so that your concentration of standard protein is on the x-axis and the absorbance is on the y-axis, and you can make a scatter plot. You then put a trend line, a linear trend function on it, and you put the r-square value as well as the y equals mx plus b equation. Regression value closer to 1 is going to signify better precision. So between these two, row E has a better trend function, a more precise standard curve based on this regression value, since it is 0.99 versus 0.95 up there. Now, you can look at the numbers that have been provided to you after you've made this first graph, and you can think about them critically, and you can see if there is an outlier within your standard trend function that, when removed, will give you a better regression value. If that is the case, you can do so, and you can get a second standard curve which has a better regression value, so it will be more precise for your actual quantifications. Now, once you've done that, you want to then think about the range of your standard curve. You need to identify that. So the range of your standard curve is going to lie within the lowest and the highest parameters for the standard curve that you used. That goes both for the absorbance as well as the concentration. So in the case of our standard curve, the absorbance range would be from 0.25 to 1.5. Now, if you change, or 0.25 to 2 milligrams actually, if you change the parameters so that you remove the lowest or the highest point, then the standard curve range would shrink to exclude those points that you removed from the system. So in this case, if you remove the 2 milligrams per milliliter, it becomes to 1.5 instead of 2. Similarly, for your concentration, for your absorbance range, it would be the absorbance for your lowest concentration of the standard protein and the concentration of the absorbance of the highest concentration of the standard protein, and that would be considered the standard curve range. In this case, the range of this standard curve, the better of the two, for absorbance is from 0.012 to 0.877. So it is going to be able to quantify proteins in samples that have an absorbance within those numbers. That's what you want. The number should be within that range. Now I've placed this again on this one so we can look at that, and I've given you the range for the absorbance for that particular one. And we have our y equals mx plus b equation. So the first thing you would do is take your y equals mx plus b equation and rearrange it to solve for x, since that is what your goal is going to be at the end of the day. So when I do that, I have my new equation, which I can then use to input into the Excel for calculation of my unknown proteins. Next, you're going to look at your blank corrected absorbance data for each one of your unknown samples. For your unknown samples, you've been provided with three dilutions per sample. You have a 1/10, a 1/5, I am wrong. You have a 1/5, you have a 1/2, and you have an undiluted sample. In my example, I'm giving you a very different dilution set, so please be mindful of it and use the dilutions that are provided to you in your actual assignment. So in this example set, I've been provided with you your undiluted sample, so it's just the sample by itself. And then I have a 1/10, a 100, and a 1000. So these are probably serial dilutions of proteins. When you look at them, the first one gave an absorbance, a blank corrected. So I've already removed the water-only absorbance from there. Gave an absorbance of 1.014. And that's definitely outside the standard curve range. So this would not be a good one to use unless I have no choice. If your dilutions are not made accurately, then it is always better to rely on your undiluted sample for your numbers, because they would be the most accurate, so-called, amongst them. So we're going to look at our dilutions. I have the 1/10 is 0.242. Not quite accurate, but within the range at least. I have a 100 at 0.003 and 1000 at negative number. So definitely we cannot use the 100 or 1000. You could use the one undiluted, but it is knowing that it is outside the range. Or you could use the 1/10, knowing, taking the number with a grain of salt, knowing that it isn't done in the most accurate manner. So I go ahead and take my 1/10 sample, I calculate my X, and I get 0.414. That's the concentration of protein in this diluted sample in milligrams per milliliter. However, I did not use this sample by itself. This is a diluted sample. So I need to take the dilution into account. To do that, I need to multiply by the dilution factor, which is 10. So I will take my number, I'm sorry about this typo, which is 0.414 multiplied by 10. So my answer would be 4.14 milligrams per milliliter. And that would be the concentration of protein in my undiluted unknown sample. That's what you're going to do for each one of the protein samples that are given to you in the example set, in your actual assignment. So once you have those numbers, you at least know how much protein was present in each one of your treatment samples within the assignment. The next thing you're going to do is look at an activity of a specific protein. What we're going to be looking at is caspase 3. Caspase 3 is the last protein to get activated in a long list of, like a long cascade of protein reactions that lead to programmed cell death response in a cell. These can happen through extrinsic or intrinsic mechanisms. So there are multiple pathways that can lead to this response, and that's dependent upon what type of toxin the cell is exposed to, what type of damage is done to the cell, if it is a drug molecule, radiation, UV, or something else, something happening, injury happening to the cell that's leading to the response. Regardless of what it is that causes the response to occur, the very, very last protein in all of those pathways is caspase 3. Once it's activated, it would lead to cell death. So what we are going to do to look at the actual cell death response through programmed cell death is bypass all the other proteins and just focus on caspase 3 activity itself. To look at that, we are using a colorimetric, results from a colorimetric assay, in which it is taking the advantage of the sequence recognized by caspase 3 in proteins. So once caspase is activated, it recognizes a very specific amino acid sequence, which is DEVD. This is the sequence of amino acids, and it cleaves after anywhere in the protein you see a DEVD sequence present. So it cleaves right after those, causing those proteins to get destroyed and leading to further cell death response. Now in this assay, there is a special substrate that is created where you have the DEVD peptide conjugated to a PNA molecule. This PNA molecule is detectable when it's released by changing color of your solution to a yellow, which we can look at by looking at the wavelength absorbance at 405 nanometer wavelength. So this is your 4 amino acid sequence, and then the PNA is added to it. The caspase 3 enzyme, active enzyme that you will have will be from the actual extract itself. So you have in your assignment, you have provided with 4 different samples. Those 4 extracts will be the source of your enzyme. The more activated enzyme is there, the more DEVD peptide is going to get cleaved, the higher the absorbance value will be. So, which is why it was important to do that standard curve and quantify the protein. Since we are not starting off with the same number of cells or the same amount of protein, the raw numbers we get for this from the spectrophotometric analysis are not going to mean anything. Since in some cases I gave it 100 molecules, the other cases I only gave it 10. So we have to relate them and create a relative caspase activity once we have these numbers prepared. So to do that, the first thing we had to do was quantify our experimental protein samples, which we just talked about. Next, we are going to convert those numbers into a relative protein amount compared to our untreated control. And then we will use our raw caspase 3 numbers and adjust those numbers by using the relative protein amount as our way for adjustment. So you have been provided with a chart to keep those numbers on track. You will write in your samples, the 4 samples that have been provided, and their respective protein concentrations that you have calculated in the first part of your assignment. You will convert those numbers from milligrams per milliliter to micrograms per microliter. So just quickly to recap for metric conversions, 1 milligram is equal to 1,000 micrograms. 1 milliliter is equal to 1,000 microliters. So since the ratio remains the same, these numbers will be the same. Once you have converted them into micrograms per microliter, you will then calculate the amount of protein present in 50 microliter of sample. So this is the amount of protein in a single microliter of sample. You are going to multiply that number by 50 to get the total amount of protein that we added into our assay for the activity analysis. So those multiplied by 50 numbers will go in here. Next, you will look at relative protein amount. To calculate relative protein amount, you are going to divide all your 4 numbers with the number in the top untreated well. The untreated number should become 1 because that's going to be considered our baseline, and then everything else is going to be above or below 1 depending on if you had more or less protein than your untreated control in a given sample. Your caspase 3 activity numbers are provided to you after blank correction. So you are going to put in those numbers as is into this next column. And to do your relative caspase activity, you will take your caspase numbers and divide them by relative protein amount. We are going to go over these a little bit in our Zoom meeting that week as well, or in the class, depending on what it is, how it is that we're doing it this semester. And you will be able to follow along with me a little bit as well. However, the calculations are supposed to be done by you independently. I will only be demonstrating how to use Excel to run those analyses. So I'm going to pause this here and show you a couple of steps in the Excel right now before I leave as well.